Ha! Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large, and this is a syringe. You might know syringes from when you get a needle at the doctor, but syringes are used all the time in science because they let you measure very precise amounts of fluid. Now check it out. You push the plunger down, and it comes out the top. Or you could pull the plunger in, and it would suck more fluid in this way. But check this out. I've got a syringe attached to a hose here, and this hose is filled with water. And I wondered, if the hose was really, really long, how hard would it be to push this plunger down? Of course, I don't know where the end of the hose is because it was really long and I had to string it all the way around, so, here it is. Okay, so let's find out. Push the syringe down and water will come out the other end of the hose. Pretty cool. You see, this is called hydraulics. Hydraulics is a branch of science that deals with fluids like water. But hydraulics are also a mechanism used in a lot of machines. Check this out. This is a syringe with a short hose on it, much shorter this time. And I press down on the plunger of the syringe and water comes out. And I pull in on the syringe and water goes back in. Because the plunger is airtight, it allows me to push or pull the water. But what if I close the system and take another syringe and attach it to the end of the hose like this? Well, then, if I push this plunger in, this syringe fills up with water. And then I pull this plunger out, the syringe empties. So check it out. This plunger raises and lowers based on what I'm doing with this plunger. And you know what that means? We've made a remote control. Huh? Check it out. So, if you take two syringes and you take a hose and you attach them to something you want to remote control, voila, you can build something like this. We have made our very own robotic arm that you can power remotely with hydraulics. Pretty cool, right? If you want to build one of these yourself, here are the materials you need. First, you need two supports and the arm. I used pieces of wood, but you can use wooden spoons, rulers, or pencils. You'll need some craft sticks, elastics, and a paper plate. And of course, two syringes and a hose, which you can get in an art supply store or a hardware store. Here's how you build your own hydraulically powered arm. First, make the base by tracing holes for your supports the width of a craft stick apart. Cut out the holes and use a craft stick and elastic to secure the supports underneath the plate and on top. Then add some elastics and a piece of craft stick in the middle so the supports won't scrunch together. Because we are holding this whole thing together with elastics. Then get your syringe in there and keep it propped up with more elastics. Then get your arm and slot it in between the supports. The arm should be horizontal when the syringe is half full. Elastics to attach the arm and the syringe. Then push down on this end of the plunger and, ha-ha, you have a remote-controlled robotic arm. You can also max it out even more by adding more degrees of movement. You can make the arm rotate side to side. You can even add a little claw attachment at the end and power it all using syringes. Haha, science and hydraulics. So let's max it out. I just need an expert to help me. Let's see. And over that way. Chris from Logix Academy, of course. Logix Academy knows all about building robot stuff. I'm sure Chris can totally help me. Let's go.
Oh, hey, Phil.
Oh, hey, Chris from Logix Academy. Great to see you.
What took you so long?
How long was I gone?
And what's with the orange lab coat?
Oh, it happened again. It keeps changing the color of my lab coat. But this time, Chris, I prepared for it, and I wore another lab coat. See?
Blue?
No! Well, you know what? This is happening a lot, Chris. So I wore another lab coat under this lab coat. I'm gonna have to wear a lot of lab coats, though, because this is happening all the time. We should talk about hydraulics, right?
Okay, yes.
Yeah, because we got some cool stuff planned. Okay, so we're just gonna get the table in here. Oh, okay. This is the hydraulic arm. Check it out.
Oh, very cool, very cool.
If we want to max it out, what can we do? We can make it bigger, we can make it
What if we did it so that the force you put on this side gets multiplied so that this side's even stronger?
Ooh, what do you call that when that happens?
Force multiplier.
I like that. Force multiplier, it sounds like a video game. So we would have a lot more power.
You have a lot more power, which we can do fun stuff.
Yeah, so if we had like lots of power, what would we do? We'd like crush something.
Yeah, let's crush some stuff.
Yeah, we could crush some stuff. Okay, can we start with syringes though?
Yep.
And then we'll work up as we go.
I like it.
So what do we need? Do we need different sizes?
So yeah, I was thinking we need a small
A delicious plate of cheese and crackers, my favorite snack. But these crackers are pretty salty, so I should probably pour myself a glass of water first, huh? No! My cheese and crackers! Why? Why does this happen? Why does the water stick to the glass? Well, because of science. And the reason why it happens gets a little complicated, but it boils down to this one simple thing. Water likes to stick to things. Huh? Did you see? Did you see how it stuck? No, of course you didn't. You know why? Because it only sticks on a small scale. See those drops of water? That's water sticking to the surface. But it only works when the surface tension of the water is less than the force of gravity, which is why water drops fall when they get bigger. So it sticks to things. That still doesn't explain why you can pour water out of some containers without any drips, and other containers make it nearly impossible. It's all about the angle. Water will flow very easily when there isn't a large change in direction, like around the curved top of this glass. But when there's a big change in direction, like at the mouth of this teapot, the water can't make that turn as easily. This is also why pouring from a full glass is much messier than one that's less full. Pouring out of a full glass, the water only needs to change direction this much to flow down the side. But from a half-full glass, the water would need to change direction this much. So all this happens because water likes to stick to things. So let's do an experiment and coat this glass with hydrophobic spray. Now, hydrophobic coatings repel water. So if it's repelling the water from the outside of the glass, will we still have the same problem? Well, let's find out. Hydrophobic coated glass, non-hydrophobic coated glass, or just regular glass. Water likes to stick to surfaces, but it can't stick to one coated in hydrophobic coating. That's impressive. Should we try something else? Well, that's one way to solve the dribbling glass problem. Except you can't coat your glasses at home with hydrophobic coating because it's not good to eat. The secret is using a container that has a very sharp angle between where you're pouring the water and the underside of the glass, like this jug. And there you go. Now I can enjoy a nice glass of water with my cheese and crackers. Oh, right, I am. Wait, hold on, I will remake the crackers into, see, look, see, it's fine. It's fine, I'm not really gonna eat that, I'm just kidding. Chris and I are maxing out our hydraulic crusher.
Yes. Before we get to that, I have a little game I want to play.
Okay, great.
Great. You can pick either the small one.
The big one!
Okay.
So what's the game?
Simple thumb war. I'm gonna press down on this side, you press down that side, we'll see who wins.
Okay, are you ready?
Yeah.
1, 2, 3, go! Oh, wow, that was really tough. Why was that so hard?
Well, Phil, I'm just really strong.
Wait a minute. My turn. Okay, 1, 2, 3, go! Yeah! See, pushing down on this one is way easier. You wouldn't think that the small syringe would be easier. Why is that?
The reason for it is that you have to push this one down a lot farther than you have to push this one down.
Let's see.
See how far this one goes, and this one's barely
This one
moving?
travels much more. This is how we can exchange a little bit of force over a long distance.
That's right.
To a little bit of distance at a lot of force.
That's exactly right.
Just like the lever, it's a mechanical advantage. But in this case, it's hydraulic advantage.
That's right.
Chris and I push down on small syringes, which gives us more force on our larger syringes. Our crusher was ready to go. Ooh, how about an orange? 1, 2, 3. We squeeze down and... Then we tried a walnut. Are you allergic to nuts?
I am not.
1, 2, 3. When we tried a golf ball, we reached the limit of what our plastic syringes and our hands could do. We need to come up with a stronger, more awesome crushing machine using hydraulics.
That's right. I have some ideas.
Okay, good. We can use metal.
We can use metal.
And we
we can go bigger as well.
Ew, this water is gross, but I'm gonna drink this water. Why? Well, because of science. No, but I'm not gonna drink the water like this. First, I'm gonna use the power of science to help me clean it. How? By using gravel. Gravel, yes, gravel. So, say I've got some dirty water, and there are particles floating in that water. Large particles, your rocks, your wood. These styrofoam bits will act as the large particles. You pour it into the gravel, and the large particles get filtered out. See? Nothing but clean, clean water. Yeah, I know what you're thinking, Phil, that's not really clean yet. That's because we haven't done step 2, sand. Sand? Yes, sand. Let's say that these plastic beads are small particles. That filters out the tinier stuff. There, huh? Clean, right? No, it's not very clean. So, we filter the water in the next step with charcoal. What? Charcoal? Yes, charcoal. Charcoal works just like gravel and sand, except on a microscopic scale. Say these bits are tiny particles you can't even see. The charcoal catches these like the sand and gravel caught the larger particles. This is called a gravel, sand, and charcoal filter. The gravel catches the big particles, the sand the smaller ones, and the charcoal the microscopic ones. These kinds of filters are used all over the world to clean drinking water. Delicious. Science.
Max Historica.
This is Archimedes.
What? Who said that?
It's me, the narrator. We're doing a segment.
Oh, well, I was working. Don't sneak up on a guy like that.
This is Archimedes, an ancient inventor and one of the greatest scientific minds ever. One of his famous inventions was the Archimedes screw, which was used to make holes in wood.
No, that's not what it's for. It's for water.
Right, used to make holes in water.
What? No! Look, did you even do your homework?
Hold on, it's here somewhere.
Look, I'll just show you. You see, in ancient times, we had many uses for something that could lift water up. From a well, or to take lake water from the lake and put it into a farmer's field, and that sort of thing.
Okay, I've got it from here. So, Archimedes invented a screw, and he drilled a hole in the side of that container.
No. Look, just sit down. I'll explain it, okay?
I am sitting. I'm in a voiceover booth.
Good for you. Now be quiet. Now look. What you do is you put the screw in the water like this, and then you want to raise the water higher, you see? And so turn it around like so, and the water fills each gap in the screw, and it starts to come up. It gets to the top, and look at this. Look, we've got water coming at the top there. The water is being pumped up. It is the first water pump.
I see. Still seems like a lot of work to fill a glass, but it's very cute.
No, we made them bigger. We obviously were not going to make them this big. This is not very useful.
Right. Archimedes, one of the greatest scientific minds ever. Chris and I are maxing out a hydraulic crushing machine. We tried one out of plastic, but now it's time to make one out of metal. These are called hydraulic cylinders, and they work the same as our syringes. Small ones on this side with a lot of travel, and then a larger one on this side to multiply the force. And some mechanical advantage with a lever to help us push even harder. We tried crushing a watermelon, and it worked great.
So what else do you want to crush?
We crushed a coconut.
It's cracking. Oh, there we go. Oh, it's gonna leak.
And then a can of pop.
Science Max Cola, now in the new smaller can.
Let's really challenge this press. Perfect.
A piece of wood.
We tried to crush the wood, but we weren't able to get it to budge. So it's time to max it out even more.
I think we're gonna need like a multi-story industrial-sized hydraulic press.
You know where we can get one of those?
I do.
Awesome. This is water. Things float on water, like pool noodles and wood and toy boats. And now we're gonna do an experiment with how paint floats on water. How's this supposed to work again? Oh! I'm supposed to take the paint out of the can first. This is a fun experiment you can do at home. All you need is a container, some water, and paint. But not just any paint, special paint you use for hydro dipping. That's hydro, meaning water, and dipping, meaning dipping.
Carefully pour the paint on the water and add a few different colors. Then take a stick to swirl it up into a pattern.
Then you get something you want to paint, and you carefully put it in like so. But don't pull it out as soon as you get it in. You have to spread the paint away because it'll stick when you bring it back out. And then when you pull it out, whoa! Hydro dip. Let that dry, and then you have a very cool painted toy. Let's do some other stuff. This is a bike helmet.
If you put tape on what you're painting, you can remove it later to make parts that aren't painted.
Skateboard. Whoa! Oh, that's pretty cool. Now to max it out. Hydro dip pants.
Wearing the pants when you do this is super messy and not something you should try at home. But the results weren't bad.
Science pants! Science pants! Science pants. One of the ways you can experience the power of water is watching it wash away dirt. You can experiment with this yourself by making your own erosion table.
To make your own, fill a plastic tub with sand and tilt it up. Cut a hole in the tub at the low end and put a hose with a trickle of water at the high end. Then to complete your model, fill it with
A little happy town.
This small model shows how rivers cut their course to the ocean by following the lowest point. Try to design your town and the layout of the ground so the river goes around the buildings.
I'll see you later. I'm gonna take a swim in the river now.
There are lots of ways to experiment. Change the amount of water, or the steepness of the angle,
Look at the soil, it's all getting eroded over here.
or the way the town is laid out.
Every time you do it, the river goes in a different direction,
And have fun.
Oh, phew, I'm tired. I'm just gonna lie down.
and that is the power of water.
Chris and I are maxing out a hydraulic crushing machine.
What about this? Is this what we're gonna use?
We went to the Natural Resource Canada's CanMet Materials Laboratory, which is a federal research lab.
Oh, this is good. Oh, look at that! Oh, is this what we're using?
No, Phil,
Oh, I
it's
can
actually-
use this. Hold on, let me figure this out.
Maybe later.
Really?
It's just over here.
CMAT is the largest research center in Canada dedicated to metals and materials research.
This is it.
Oh,
This is it.
yeah, right! Hydraulic press. How much force does this apply?
This can do 2 million pounds,
That's over 900,000 kilograms.
which is about 20 cars.
Let's crush some stuff! Oh, crushing! We gotta get the stuff. We gotta get the stuff. Okay.
We started out with the piece of wood which defeated our last press.
And go!
that sound.
Awesome. Reversing.
It turned our wood into a pancake.
Whoa, totally flathead.
So it was time to try some other stuff. We crushed a ball of plasticine.
That is neat. You sort of made a rainbow.
Yeah.
Aluminum foil.
Aluminum foil.
Yes, it is now a solid plate of aluminum.
And a basketball.
Basketball. Good thing we got these earplugs in because when it pops, it'll be loud.
What?
Never mind.
This hydraulic press was so maxed out, we had to think of the toughest stuff to crush. We crushed hockey pucks, a safe, we crushed a hydraulic jack with the hydraulic press.
This is a metal vise. Hard, strong,
Yeah, it's steel.
heavy steel.
Whoa, look at it bend. Wow.
Now it's time to crush a bowling ball. It totally loaded. Science Max, experiments at large, hydraulics. Whoa, nicely done.
So fun.
I should reverse it and we should start cleaning all that stuff up,
Yeah,
huh?
I think so.
Okay, reverse. Greetings, Science Maximites. My name is Phil, and today on Science Max Experiments at Large, we are using mouse traps, but I cannot find my mouse traps, so it's gonna be a little hard to do the experiment unless I have... Oh, hey, here they are. Oh yeah, I stored them preset. Why would I do that? Okay, well that's fine. Anyway, today we, careful, are going to be using mouse traps. Like I said, we are going to be using mouse traps. Mouse traps as a form of propulsion. That's the force that makes things go, and we are going to be making a boat go. And what is the thing that's going to make this boat go? A mouse. Oh, it's not set. Sorry, I'm really jumpy. Anyway, we're gonna be using a mouse trap. And don't worry, no mice are gonna be harmed in the making of this or any Science Max episode, but mouse traps are really great because they can store energy in the spring. If you see, there's a spring that makes this bar want to snap back, but we can put energy into the spring and store it and then use that energy as it unwinds the spring to propel our boat. But it's a little more complicated than just this, so come on, I'll show you. What we're gonna do is build this. This is the mousetrap boat, and it works like this. I've got the mousetrap, and it's attached to a long arm. That arm has a string on it, and it goes around the paddle wheel, and as the mousetrap unwinds, the paddle wheel spins like that, which pushes the boat forward. Now, it looks kind of complicated, but it's actually quite simple to make, and here's what you need.
My mousetrap boat is made with styrofoam, craft sticks, and elastics. You'll also want a pencil, plastic drink caps, a shish kebab skewer, small zip ties, string, and of course your mousetrap. Now, mousetraps can hurt your fingers, so get an adult to help you when you use them. Start with 2 pieces of styrofoam. I like to cut mine into this shape, but the only really important thing is that they're the same size. Your paddle wheel is made from a circle of styrofoam with it penciled through the middle, and it will go across like this. To make the paddle wheel, I use cut pieces of craft stick.
Or they can be plastic, and make some cuts and then put them in like this, and that is what will make your paddles on the paddle wheel, because that's the wheel and that's the paddle wheel. That's why they call it that.
Stick drink caps to the ends of the pencil after sticking it through the styrofoam. I like to use a few craft sticks and elastics to help give the styrofoam strength. Next is the mousetrap, which you want to glue down to a frame of 4 craft sticks. Attach the frame to the boat with elastics, then attach the shish kebab skewer or a pencil to the mousetrap with zip ties. I like to put some craft sticks on the end to make it easier to tie the string to it. Wrap the other end around the paddle wheel pencil, and remember you need enough string so that your stick can lie flat.
Okay, let's try it out.
Wind up the paddle wheel. This will be a little hard as the spring will pull back, but that's where you're storing the energy. And when it's wound up, put it in the water and
Let it go. The paddle wheel turns because the mousetrap is transferring energy that we put in earlier, and it goes all the way.
we stored the energy in the tension of the spring. Now that tension is pulling the mousetrap, the stick, and the string, which turns the paddle wheel and makes the boat go.
Mousetrap-powered boat!
If you want more detailed instructions or other designs, look up Mousetrap Boat.
And there you have it, the mousetrap-powered paddle wheel boat. And this is what we're going to max out today. Come on. All right, time to pick an expert and go off to max it out. Careful. Okay, let's see here. And, who to pick? Michaela from the Ontario Science Center. She'd be perfect. All right. Come on. I ended up in the water again. Oh, well, at least maybe Michaela made it. Oh, Michaela!
Whoa, Phil!
Are you okay?
Are we still fixing the portal?
Yeah, I needed to. We
man.
could just a little bit. It's a little off again. Anyway, great to see you, Michaela from the Ontario Science Center. You're gonna help me max out the mousetrap boat.
Awesome.
Yeah.
Wait, where's the boat?
I don't have it. I thought it was gonna come through the portal. It could be anywhere, really. I mean, what? Oh, here it is. Okay, good. So here is the mousetrap boat. Check it out. So I got a mousetrap here, right? And you wind up the paddle wheel, and it goes. Yeah, right on.
Awesome.
So what do you think we should do in order to max this out?
Well, first idea, I'm just thinking more mousetraps.
More mousetraps. So we just make a boat and it has like N mousetraps on it.
At least.
Okay, great. Actually, I had mousetraps coming through the portal as well.
Okay.
Oh. Okay, we're all right. Okay, so now we've got the mousetraps. We can start building. Let's collect them carefully, though. I don't know if they're...
Initial thrust or constant thrust. What's the difference? It's all about power. Paper airplane initial thrust. It gets all of its thrust from my throw. Initial thrust. If you want constant thrust, you have to take the thrust with you, like this. There's a lot of cats in here. Initial thrust. Initial thrust. Initial thrust. All the energy is put into the beginning of the... All the energy is put into the beginning. If you want constant thrust, then the thing has to produce power while it's moving. Wind up car, constant thrust. Actual car? Yeah, that's constant thrust because you have an engine. Of course, not this car. This is a toy car. But you know what I mean. Check out this fishing rod, and on it I have a lure with a hook. Now watch this. I cast it out, initial thrust, but then I use the reel and start winding it back in. Constant thrust, huh? Two thrusts in one. And now you know the difference between initial thrust and constant thrust. Hey, I caught a fish. Hey. Oh, easy, kitty. Nice kitties. Easy, Ramona!
Michaela and I are maxing out a mousetrap boat. We built a larger version with 10 mousetraps all in a line.
So it looks pretty good. I think we're ready, right?
Yeah, I think so.
Got a whole bunch of mousetraps. Should we wind it up and see
All right.
what happens?
Let's do it.
I think this is gonna go pretty well. What do you think of that stick? Is that gonna bend too much? Is that gonna snap or?
Looks pretty flexible.
I mean,
I think we're okay.
I think we just keep going until it breaks. Ooh. Now it's starting to look very fast.
man.
Yeah, like it looks like a speedboat. Okay, ready? Go. Well, positive. It is working.
It's not gonna win any speedboat
It
races.
is not gonna win any races at all. But it's totally working. The mousetraps, they're pulling on the string. The string is making the paddle wheel turn. Just not much. I would have thought this many mousetraps would be a little bit more effective.
Yeah, it looks like we're going for distance over power things. See,
Oh,
we're
right,
using
because-
a lever here. That's a lot of distance for this to travel. But if
Small
we
amount of force over a much longer distance, that's how a lever works.
Exactly.
So we slide the rope down further on the stick, then we would get more force, and it just wouldn't go as long. Okay, so why don't we try that? Wrapping, like that.
Nice.
All right, once again.
Trial 2.
Okay,
Okay.
ready?
Ready, set.
Go! Ah!
Hey, that looked better than last. Oh, now it's picking up.
Yeah, that's really working. Oh, careful. Oh, look out! Look out! So, good. It's good.
Hey.
It's not great. Not yet.
Yeah,
Right? How do we make it better? What do you think?
Well, I was thinking, what if we try to reduce the friction? Remember that other boat we tried?
Here it is.
Oh, yeah.
The little one, you mean?
Yeah, the little one. See, look at this one. It has a pontoon style. Do you see how we have it floating on these two surfaces?
Yeah.
So very little is actually touching the water. Whereas
Oh.
this one, we have a giant hull that's going to drag the water and slow our boat down.
So it's sort of like the difference between like pushing a whole bunch of water like that and pushing the water like that.
Yeah, we want very little resistance resistance for a boat.
So little resistance with a couple things that just stick down like that. A lot of resistance when we have big, flat, big, like that. So we completely rebuilt this boat. Shall we do it?
Yeah, let's do it.
Our tools floated away again.
Oh.
Race ya! Our maxed out mousetrap boat isn't the only way to give a boat propulsion. Let's look at another way using a balloon. Let's make a balloon-powered boat. All you need for that is something to be your boat and a balloon. Then you attach them together. Actually, the best way to do it is use a straw and attach the balloon to the straw using an elastic band. And then you attach it to your boat using more elastic bands, just like this. I've put a nice tape top on the boat to make it look awesome. And I also put a little bit of a riser here using just anything plastic to keep the straw nice and straight, because the question is, will our balloon-powered boat work better if it's pushing in the air or if it's pushing in the water? Well, let's do a science experiment and find out. First version, in the air. Oh, almost all the way. Now let's try it with the straw like this so it pushes into the water. Whoa, works so much better. Why? Because water is denser than air.
The air coming out of the straw has to push against something to make the boat move. Water has more mass than air, so pushing against water has a better result.
Now, let's max it out. This is an air compressor. Well, actually, that is the air compressor. You see, the engine here pushes air into this tank, which works sort of like the balloon. And then it goes out this long hose, which sort of works like a straw. So let's make a maxed out air-powered boat. Ready?
Just like the small boat, pushing against the air doesn't produce much thrust.
Huh. Not so great. But now let's put it in the water.
Pushing against the water gives me much more thrust because water is more dense than air.
Oh! Maxed out air-powered boat! Maxed out air-powered boat! Yeah! Whoa! That's not me.
Michaela and I are maxing out the mousetrap boat. 10 mousetraps didn't seem to make our boat go very fast. But moving the string down our lever arm helped, and now we want to redesign the hull so it has less friction with the water.
Check it out! This is the ultimate mousetrap boat. We got 10 mousetraps here. We got our long arm. We have it attached at the right point of the lever, we think. And then we've got two paddle wheels at the back and pontoons.
Yes.
Yeah, so what do you think, Michaela?
This thing is set.
It's gonna be awesome?
Yep.
Okay, ready?
Ready? Let's test it.
Whoa, it's working.
Hey,
It's working.
Picking up speed.
Yes.
Wow.
Whoa, mousetrap boat. I mean, it's good. It's good. It's not Science Max good.
Yeah. We were hoping it would go faster.
Faster
No.
or... No, pretty much just faster, yeah, okay. Obviously, we need to store more energy. That will make the paddle wheels go faster, right?
Yeah, so we just have to think about it, right? Like, what's stronger than a mousetrap?
Well, 10 mousetraps. That's why we have 10 mousetraps, Michaela.
Okay, what's stronger than 10 mousetraps?
11 mousetraps? Like, if we just keep going and
Okay,
it's
enough
gonna
with
get
the
super
mousetraps.
wide, we have 1,000 mousetrap wide. What?
Enough with the mousetraps. Have you ever seen, like, a rat trap?
No?
They're huge.
Well, hold on. I can just get one from the portal. One rat trap coming up. Oh, okay, came from, all right, well, that's fine. And, whoa!
Wow.
Yeah,
Look at
that is a lot bigger. Okay, so
Huge
snap
difference.
yours.
All right,
Is it?
ready? Mousetrap.
Okay.
Okay.
That's terrifying. So that's a lot more power.
Yeah, a lot of force.
So tell you what, we have a little mousetrap boat. Why don't we build a little single rat trap powered boat and we'll race them, and we'll just see the difference in power from one rat trap to one mousetrap.
I like that. We'll do a prototype before we make a big one.
Yeah, okay, come on, let's go.
So we built a rat trap boat to race the mousetrap boat. And then Michaela and I got a little competitive.
Check out the rat trap boat.
No, check out the mousetrap boat. Mousetrap boat is better because...
Yeah, rat trap boat is better. It's got bigger springs, more potential energy stored in here.
And mousetrap boat has less potential energy and less springs, but he's got more heart, and he really wants to win.
Hey, yeah, I'll tell you what, Phil. Loser jumps in the pool.
What? Oh, okay, sure, let's do it. Okay, ready?
Go!
So, as you may have guessed, the rat trap boat has a lot more potential energy that can be stored in the spring.
Okay, so rat trap boat is clearly better than the mouse trap boat. We make the boat the same way,
Yeah.
but we use rat traps instead of mouse traps. What do you say?
Love it.
Okay, let's do it.
Let's do it.
Yeah.
Wait a second, Phil.
What?
Ferris Ferry, gotta jump in the pool.
Okay, fine. Here you go. Hold this. Inertia. What is it? Well, it's directly related to Newton's first law of motion. An object in motion tends to stay in motion, an object at rest tends to stay at rest. Let's do an experiment. Here is an object. Right now, it's at rest. You might think that means it has no inertia, but that's not true. Inertia just means an object's tendency to keep doing what it is doing. Right now, it's doing nothing. But if I wanted to overcome its inertia, I would have to put energy in. And now that I have, it is moving on its own. It has inertia. If I wanted to stop it, I would have to overcome its inertia, its tendency to keep moving. There. I went exactly that far. Now, let's max it out. I'm adding these weights to the cart. Now it has a lot more mass, which means it has a lot more inertia and its tendency to do nothing. But this time it has a lot more inertia. If I wanted to get it going the same speed as before, I'd have to put in a lot more effort. There, now it's going the same speed as before, but now it has way more inertia, so stopping it will be harder. So there you go, inertia. A thing's tendency to stay moving or stay still, and the more mass, the more inertia. Dear Phil, I can't believe you did a whole episode on boat propulsion and you didn't use the greatest thing out there for making a boat move, a propeller. Sincerely, a fan. Well, let's talk about propellers. Oh, good thing this is fan mail. Get it? Because it's a fan? Yeah, anyway. A fan pushes air just like a boat propeller pushes water. They're both fluids and they behave in the same way. Now, if you look closely at a fan, it's curved on the blades. The air or water is caught under at this side and then it's pushed out on the curve to make it go that way. And the faster it spins, the better it works. Now, this is a propeller-powered boat. And what you do is wind up the propeller. I have an elastic band here to store the amount of energy I put in. And then you put it in the water, the propeller spins, and the boat goes forwards. It's being propelled by the propeller. That's why you call it that. Awesome, right? Well, now we'll max it out. This is a drill. It spins. And this is a propeller, and when you put it in the water and spin it, it provides thrust. So let's try it out. Whoa!
Remember not to try this at home. I am a trained professional.
This is a very small propeller. Let's compare. This is a super maxed out propeller. Whoa, okay, let's try it out. Whoa!
The larger a propeller is, the more energy you need to turn it, and the more propulsion you get out. Michaela and I are maxing out the mousetrap boat. Well, actually, we can't call it a mousetrap boat anymore because now we're using rat traps. The design is the same as our 10 mousetrap boat.
Rat trap boat! Rat trap boat! It's the super most rat trap boat ever!
We wind it up and try it out.
Okay, ready?
Go!
It worked great. The reason is because this boat was storing a lot more energy in the spring tension. More energy means more propulsion. So much we couldn't even catch it.
Yeah!
Let's do it again.